Hey folks, still at an airport in China and still have a couple of hours to kill before I have to do my next flight. So I thought I'd do another post on the weirdness of infinity. And today we'll talk about how some infinities are in fact bigger than others, in contrast with part one where we looked at a lot of infinities that are all exactly the same size. So as a brief refresher, to compare the sizes of different infinite sets, we talked about the idea of setting them up in one-to-one correspondence. We use the idea of a set of M&Ms, for instance, that if we have a big stack of M&Ms and we want to divide it as equally as possible, we'll keep lining up M&Ms next to each other to make them one-to-one to see which stack runs out first. In this way, we can show that the set of counting numbers, 1, 2, 3, 4, 5, 6 to infinity, is the same size as the set of even numbers, 2, 4, 6, 8, 10, and so forth. The set of prime numbers, 1, 3, 5, 7, 11, and so forth. We can even show that the algebraic numbers, which are the roots of algebraic equations, also are the same size as the counting numbers. They can also show that fractional numbers, 1/4, 1/3, all of those numbers are the same. The set of all of those is the same size as the counting numbers. So are there any infinities bigger than the set of all counting numbers? And in fact there is, and there are. And let's take a look at one and we'll show you how we can prove it's bigger. The set in question is the set of all numbers on the number line between 0 and 1. So all points in between. We call it the continuum. It's a continuous string of decimal numbers ranging between 0 and 1, but not including 0 and 1. Now the first thing we can do is set up an interesting different type of one-to-one correspondence to show that the set of numbers between 0 and 1 is the same size as pretty much any interval you want of the real numbers between minus infinity and infinity. In particular, if you want to show that the numbers between 0 and 1 constitute all the numbers on the real line between minus infinity to infinity, we set up this geometric construction. We put a kinked line segment at the origin of the real line with kind of 0 to 0.5 hitting the origin of the real line and 0.5 to 1 slanting upward from there. We draw a dot right between, or a point right between the 0 and 1 on the triangular segment, and then we draw a straight line from that point to any point on the real line we want, or through any point of the real line we want. And this creates what we call a mapping. It says that that line, that red line that we draw, intersects both that line segment between 0 and 1, and it intersects the real line. And we can argue there's a one-to-one correspondence. For every unique point that we intersect on the line between 0 and 1, we also hit a unique point on the real line between minus infinity and infinity. So again, you might be thinking, well, this seems like a bit of a trick because now you're showing me all these infinities of the same size again. But now let's try to map the numbers between 0 and 1, which we call the continuum, to the set of counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, and so forth. Here we're going to get one of the most beautiful constructions in mathematics, in my opinion, done by Cantor, and it's so beautiful because you can pretty much explain it to anybody. You don't need any really special math to do it. So here's the Cantor construction. First of all, let's imagine that every number between 0 and 1, we write it in terms of an infinite repeating decimal. So the A's and the B's and the C's and the D's in these cases are all, decimals between 0 and 9. And so we, on the right, try and create a list of every decimal number between 0 and 1. And in order to make a one-to-one correspondence, we want to argue that that list on the right can be mapped to the set of natural numbers. So we can set up that one-to-one correspondence. That 1 can be set to one decimal, 2 to another, and so forth. But here's the cool thing, and what Cantor did. He now said, suppose we've got that list of numbers that matches the counting numbers. Now let's construct a new number. And we construct that new number by making its first decimal be anything other than A1, its second decimal anything other than B2, its third anything other than C3, and so forth. And in the end, we can use it to construct a new number. And that new number cannot be on the list we constructed at all, because the number disagrees with one decimal of every number we have on our list. So we've constructed a new number not on the list. So the reasoning here is a proof by contradiction. Cantor said, let's assume that we can make a one-to-one correspondence between the counting numbers and the continuum. And then he showed that, no, you can't do that. No matter how you try, you will always be able to find additional numbers that are in the continuum that are not in the counting numbers. So the continuum is in fact a bigger set than the counting numbers. But this leads us to other really weird and counterintuitive conclusions. For example, is the set of all numbers that lies within a square, which we can kind of indicate by coordinates x and y, is the set of all numbers in the square bigger than, smaller than, or the same as the set of all numbers on the real axis between 0 and 1? Well, here I borrow a little bit from my blog post on the subject. Let's imagine again we write the x-coordinate as a decimal, 0.x1, x2, x3, the y-coordinate as 0.y1, y2, y3. Now we construct a new number. So every point in the square can be labeled by an x value and a y value. But now we construct a new number on the line segment between 0 and 1 by putting together x1, y1, x2, y2, and so forth. And with a little bit of extra thought, you can convince yourself that you've made a unique mapping from the square to the line segment. And we can go further. We can map a cube to a line segment, and we can map a 4-dimensional cube to a line segment, or a 5-dimensional. So we could say an finite n-dimensional cube has the same number of distinct points as the line segment itself. The fact that the real numbers are bigger than the counting numbers leads to a really surprising result. And here's a little hierarchy that I kind of adopted from an old math book, that we've already said that the natural numbers, or the counting numbers, or the integers, have the size of the counting numbers, which is typically labeled aleph 0. Well, we've seen that the fractions are also aleph 0. All rational numbers, which includes the natural and the fractions, are also the same size infinity. The algebraic numbers, I didn't prove it, but I mentioned, also are size aleph 0, which also means that irrational numbers are size aleph 0. But the only thing that's left that's not included in the algebraic numbers and that is included in the real numbers are transcendental numbers. Transcendental numbers are those numbers that, like pi or the exponential e, these sort of unique numbers with a non-repeating pattern. And we only know of a very small number of transcendental numbers. But the mind-boggling thing is, apparently there are more transcendental numbers than fractions, integers, any other type of number we could imagine. We can in fact go even further, and we can argue that there are sizes of infinity bigger than the continuum. And in fact, we can construct a hierarchy of infinities where the counting numbers are smaller than the continuum, which is smaller than the next one, smaller than the next one. And I won't prove all that, which is included in one of my old blog posts. But in the next post in this series, I want to return to the counting numbers and the size of infinity there, and show you something that you may have never heard before. People talk about these infinities all the time. I'll tell you about something related to physics and optics and infinity that you've probably never heard of before, so stay tuned.